quantization,
sampling.
Then we talk about at first we talk about the sampling. Then in the next lectures we talk about this quantization and the encoding, right? And the quantization means giving some values to the sampled signals, that is round up close to the sampling value. We call it quantization voltage. And then we will see that we can make it to give some coded value, right? So those part of quantization and coding is actually can take place by this circuit. So this analog to digital conversion, today we'll discuss, it will be cover how we actually quantize to keep some values and get some coded value, corresponding coded value. So there are different techniques of analog to digital conversion. We will start first with the known as a slope ADC. A slope ADC, a single slope, dual slope. So usually it is a dual slope ADC. But to understand this dual slope ADC, at first we need to go through a single slope ADC. We don't use the single slope ADC, but to understand the dual slope ADC, we will go through a single slope ADC first. Okay. In this single slope ADC, we will use an integrator circuit. We will use an integrator circuit. An integrator circuit is an open circuit with an RC. This is an open circuit. So in the open circuit, it can be used an operator, like operator, addition, subtractor. So here we will use as a comparator. In the open circuit, we have two inputs, one output. So also we have another input DCC plus DCC to minus DCC. But usually we have two inputs. One is inverting input, another is non-inverting input, and then we have output. So here we are using the inverting input. We are giving our input signal to the inverting input, and we are connecting to this non-inverting input to the ground. Anyway, so whenever it will give you the result, the output, with time it is give you a negative slope. It will give you a negative slope. The output will give you the negative slope. Okay. Why we use this dual slope ADC? Can you see this one? Because today I am using only the board. Or maybe you can this side. So this is an integrating type of ADC. So dual slope ADC is known as an integrating type of ADC because we are using the integrator circuit. And this type of ADC provides high resolution and good accuracy. So these are the advantage of dual slope ADC. One is the high resolution and the accuracy. Because if you can remember, when you talk about the quantization voltage, there is always a quantization error, right? There is always some quantization error. So if we can reduce the quantization error, we need to increase the number of bits. That means resolution will increase. So with our dual slope ADC, we can achieve both things, the high resolution and the accuracy. But the trade-off, what is the trade-off? Trade-off is the conversion time, very slow. Conversion time is our disadvantage, or you can say trade-off. This is the advantage. So for example, they are not, as they are, trade-off is the conversion time is very slow, so they will not use for data acquisition. For example, in signal processing. In signal processing, we will not use this dual slope ADC. So why we can use, as you can see, the advantage of this dual slope ADC is accuracy, and the resolution we can use in the measurement device, like digital voltmeter. We all use the digital voltmeter in our lab. So inside the digital voltmeter, we actually get the value of like 0.1 volt, 3 volt, 2 volt. It is showing you the digital value, but it is actually measuring your continuous signal, right? Continuous amplitude of the input signal. So in the digital voltmeter, we use usually dual slope ADC, because this dual slope ADC will give you the accurate value and it will give you the high resolution. That's why it will give you the accurate value. And if it is take long time, it is not matter to us, because we are not giving for signal processing a bunch of input signals are not giving. We are just giving one signal at a time. Okay. So So this is the use. As I mentioned, to understand this dual slope ADC, at first we will discuss about the single slope ADC. A single slope ADC. So let's start with a single slope ADC. So if I draw the single slope ADC, it will consist of a comparator and an integrator circuit. So we already saw this integrator circuit. This is my integrator circuit. This is R, this is C, and this is the output of the integrator circuit. And the output of this integrator circuit will give it to the comparator circuit. So we will give it to another operational amplifier open, and it is the comparator circuit. And here we will give our input voltage to compare. So this is the integrator circuit. And this is the comparator circuit. So the comparator circuit will compare this input voltage with the output voltage of the integrator circuit. Because here every time we have two input signals, right? So here this is the comparator, so it will compare the input voltage with the output of this integrator circuit. And the input signal is given to non-inverting signal, and here this is the reference voltage. This reference voltage is given to the negative terminal of the comparator circuit. And this is also another thing, we have to make sure that this is a negative voltage. This reference voltage is a negative voltage. Okay. So this is overall circuit. Okay, the first thing, as I mentioned, this reference voltage is negative. We give it to the negative terminal of the integrator circuit, and the output of this integrator circuit will be given to the comparator circuit. And in the comparator circuit, my input signal is given to the non-inverting terminal. Then we get the output of the comparator. So then compare this input voltage within the comparator. So what will be the output? Output of this integrator circuit. As I just showed you that the output of the integrator circuit is a slope, right? So if I think this one, so this is the in, for example, and this is the time. So we can say that this reference voltage integrate until the integrated output is equals to the input voltage. Because this is the comparator, right? So this integrator will integrate your reference voltage until the output of this reference voltage, integrated voltage, is equals to your input voltage. So it will start to integrate. It will integrate until when? Until it reaches to its input voltage. So it will take some time. For example, this time is t. Okay? So again, what is this one? This is the output of our integrated circuit. And this means it will integrating our reference voltage until it reaches to its input voltage. So maybe you will think why it is now positive, because in our previous graph, I show you it was negative, right? How it works. And we can say that this time t is actually equivalent to our input voltage. This time t is proportional to our input voltage. How? Let's see. So if I want to write the equation for this output of this integrated voltage, we can write down V out is equals to minus 1 over RC integrated of minus V reference of dt, because this circuit will integrate with respect to time, and we give some negative voltage, and we are given to the negative terminal, so that's why it is negative. So this negative and this negative will become positive. So that's why it is positive, the first thing. Okay. Now, as I mentioned, that this time is equals to or proportional to our input voltage. Now we need to prove that this T1 is equals to V1, right? So what we can write down here? We can write down here this integration circuit minus 1 over RC integrated of minus V ref into dt is equals to what? T times V reference by RC. Right? T times by reference. If you do the integration, it will give you this one. And it will reach to where? V in. So it is equals to V in. Now, if you look at this circuit, in the single slope ADC, this V reference and this R and C values are constant, are fixed. Because you will give this R value fixed, this C value is fixed, your reference voltage is fixed. Because you have to take some reference voltage, right? Those are fixed. If those are fixed, we can see here this T is actually so if you can measure the time, it is actually give you the input voltage. So we can say that from the graph, we can say that at time t, the output voltage, from the graph t, the output voltage, at time t, the output voltage is equals to the input voltage.
Is it proportional or equals?
Equal. Equal. It's better equal. If I write down proportional, then we need to put some proportional factor. It's equal. So we can say that this input voltage V in is directly proportional to T or equals to T. So this time is the measure of input voltage. This time T is the measure of input voltage. Now how we can measure this integration value? To measure this integration value, what we can do, we can extend our circuit. We can extend this circuit. Just I want to draw again, please let me draw again. I take more space. I will draw again the same circuit. This is R. This is given to the integrator. This is the capacitor. This is negative terminal. This is positive terminal is connected to the ground. This is minus V ref. This is R. This is C. Then we take the output and give to the comparator circuit.
My leg is turning
Here
into
we
wood.
get the input signal, and this is the comparator circuit. We take the output of the comparator circuit, we'll give it to a AND gate. We'll give it to an AND gate. In the AND gate, we know there will be two input AND gate, right? So what is about the another input? In another input, we'll give our clock signal. Or clock. Then this output of this AND gate will be given to a counter circuit. And this counter will give you the binary output. So when the both input is high of the AND gate, then you will get output high. Right? This is AND gate. When the both input of the AND gate will be high, it will give you high output. So we can say that if you want to provide this clock to the counter, this input should be high. If you want to provide this clock to the counter, this input should be high. And when it is going high, when V high, so the output of the comparator is given to the AND gate. Through this AND gate, the clock pulses are applied to the counter. Okay. So whenever the output of the comparator is high, then clock pulses will be applied. So it's supposed to be high. Then we can apply this is counter, we can apply this clock signal to the counter. So as soon as this counter goes, get into pulses, it starts counting. So whenever the clock pulses go there, it will start counting. And it will keep counting when? It will keep counting until the clock pulses, this output of the AND gate becomes 0. So when the output becomes 0, there will be no clock pulse, the counting will stop. So the counting will count until the counter gets, the clock pulse is fed to the counter circuit. So at the beginning, before you start the counting, everything is reset to 0. Everything is reset to 0. So whenever the conversion starts, then the integrated output will be less than the input voltage, right? So when the conversion starts, at the very beginning, this input, this one is less than this one. So that means Vin is high. So if Vin is high, output of the comparator is high because it's positive terminal. So output is high means, so it will start counting. Okay, during the conversion, that means during the conversion we can say that whenever the conversion starts, the integrated output will less than the input voltage. So we can say that during the integration time, the counter starts counting. So again, this is the integrator circuit, so it will integrate. And once it will integrate, it will give you some output, right? We already said that T1 or T is equals to this Vin, this integration circuit. Then it will give it to the integrator circuit, as I showed that, because it will reach to Vin value at T in time or T1 time. So that's why I call it, so T1 is equivalent to Vin. And this Vin is given to this comparator circuit, and the comparator circuit will give you output depending on the input, right? So if the input, Vin input is the positive terminal is high, it will give you high. If this one is high, it will give you low. So during this integration, still it is low, right? At that time, Vin is high. So here we have high. So whenever the input of this AND gate is high, this clock pulse will be fed into this counter. So counter will count and start counting and will counting. So during the integration, the counter will keep counting. Okay. As soon as the output voltage of this integrator is equals to Vin, then it will go to low. So when it will go to low, then the clock pulse will not fed into the counter. So when the counter will stop, it will stop. So until it stops, when the counter will stop, that will give you the equivalent value of the input voltage. So we can say that, so whatever count that is present at the output of this counter is directly proportional to the input voltage. As I mentioned, we need to make sure that T1 is proportional to Vin. So during this integration, it was counting. So T1 is going, it was counting. When T1 and T1 is here, V1 equals to V naught, then it stop. So that means my counting is a stop. So that means T1 is proportional to Vin. So we can say that T1 is proportional to Vin. So in this way, the single slope ADC converts the input voltage into the binary outputs. Now it depends on what? Depending on the input voltage, the time will change, right? So why it is known as a single slope? If I draw the curve, it is showing the output like that. So this is my Vin, this is my output. So here we draw three different input voltage. Every time the slope is same, but depending on your input voltage, it requires more time. So for example, this is Vin3, this is Vin2, this is Vin1. So this Vin1 is greater than Vin2, but less than Vin3. You can see the time, for example, this is T1, this is T2, this is T3. So it is required more time, it requires less time than this one. So your input voltage is equivalent to your time. So we can measure this input voltage with time. So as we are getting only one slope for the input voltage, that's why it is known as single slope ADC. But we don't use the single slope ADC. We usually use the dual slope ADC. But for understanding this dual slope ADC, we should go through this single slope ADC first. So this is the working principle of the single slope ADC. Okay. Now let's see the working principle of the dual slope ADC. In the dual slope ADC, sometimes we will have a switching circuit also here. So to discharge this capacitor, okay? There is a switching circuit. You can switch to discharge this capacitor. Okay. Now look into the dual slope ADC. If I remove this one, it's a dual slope ADC. The first stage of the dual slope ADC in the circuit, At first we will have some switch here. This switch can be connected either V in or V reference. Either V in or V reference. Okay? So move this one. Just try to understand at this first point. So still it is an integrated circuit. Now we have a switch here. It can switch to V in or V reference. At the beginning of this conversion, this switch will be connected to V in. This switch will connect to V in. That means we are giving, so this is still the negative V reference voltage. Can you see? It's fine. Can you see? Headed?
Yeah.
Is it okay?
Yep.
So we are giving this V reference to here, negative V reference, and we are giving the input voltage also here. At the beginning of this conversion, we connect this switch to the input voltage. That means we are integrating the input voltage at this time. As it is a negative, positive voltage, we will integrate into the negative side. So we can say that, so at first there is a switch at the input of the integrated circuit, and it can connect either your input voltage or your reference voltage. Initially, the switch will connect to your input voltage. Initially, your switch will connect to your input voltage. So once the conversion starts, then this integrator starts integrating. And this input signal for a finite time, and let's say this time is t. So if I draw the curve here, so when the conversion starts, this integrator will integrate your input voltage, right? And it will integrate for a certain finite time. For example, this is T1. So it will give the slope for the integration. It is not, why it is negative? Now because it is a positive terminal. And we are giving to the negative terminal of the integrated circuit. So it will give you the result like this. For example, this time, if I take this one, extend this line, this time is T1. Okay? So what is the output voltage of the integrator? If I write down the equation for the output voltage of the integrator, we know V0 is equals to minus 1 over RC integrated V in dt. So we can write down this. If I mention this is denoted by this voltage is V1, we can give it V1 is equals to minus T1 RC by into V in. Right? So this is my output voltage. This output voltage, for just for our simplicity, we denote it with V1, okay? This output voltage of the integrated circuit. V1 equals to T1 by V in by RC. So we integrate this time our input voltage. Okay, fine. So after time T1, the switch will connect to V reference. Then the switch will connect to V reference. Then it will connect to here. So after time T1, it will integrate now, which one? The V reference voltage. Now it will start to integrate the reference voltage until it reaches to 0. At first, it will integrate our input voltage, and the result is this one, at T1. For example, we take it a finite time of T1. After T1 time, now my switch connect to V reference, so that my integrated circuit will now integrate my reference voltage. Until when? Until it reaches to 0. That means this one. For example, it is T2. So this is the integration output of my input voltage. This is my integration output of my reference voltage. Okay? Fine. So this time T2 is the time that is required by the integrator to reach at 0 voltage. And this T2 is the direct measure of our input voltage. This T2 is our direct measure of our input voltage. How? Again, we need to prove it. This T2 is proportional to input voltage. Okay. So as you can see that after time t1, my integrator circuit is connected to the V reference voltage, right? So at this V reference voltage, there is some initial voltage. At the integrator, already they have some initial voltage. On top of that, now it will have this reference voltage. So we can say that at start time t2, this V out is now minus 1 over RC integrated of minus V reference dt plus some initial voltage at this time. It is actually integrating which one? My reference voltage. But before that, it has some initial voltage because we have integrated this input one, right? So this is the initial voltage. Okay? So this negative and this negative again become positive, and we can write down this one minus T2 times V reference divided, sorry, not minus, by RC. And this initial voltage is which one? Is V1 plus V1. If you put the value of V1 here, so it will become T2 by RC times V reference plus minus T1 by RC VA. Okay? So from here, and this one, after time 2, it reaches to what? 0. So that means we can write down this equation is equals to, total equation equals to 0. So we can write down T2 times V reference divided by RC plus, or minus, sorry, plus minus, this minus T1 RC V in is equals to 0. So we can cancel this RC and RC. So from here, can I move this one? Now I'm coming from here to here. So we can write down T2 times V reference by RC is equals to T1 by RC V in. Then RC and RC cancel. So as I mentioned that V reference is and T1 for the dual slope, this T1 and V reference is fixed. As you mentioned in the single slope, few things are fixed. RC value are fixed, that V reference value is fixed. In case of dual slope, this T1 time will be fixed and the RC value is fixed. So if this is fixed, this T2 is equals to this T2 is equals to, if you can measure this time, it is actually equivalent to your input voltage. That means during this time, whatever input voltage is coming, you will get the equivalent output code. Okay? So here, what we have decided, here we found that two things in the dual slope ADC, this T1 value is fixed and V reference is fixed. Another important thing is here, if you look at the single slope and the dual slope. In the single slope, we have the RC value. We have a dependency on RC. That means it can be changed with temperature. The resistance and the capacitance are very much changeable. So can change. But if you look at the dual slope AC, there is no RC value. So it now independent of R and C values. So this is the advantage. That's why you don't use the single slope. We usually use the dual slope. And as I mentioned, what is the advantage of a dual slope? The advantage of a dual slope is a high accuracy and high resolution. But the drawback is their conversion time is very, very slow. So we cannot use this dual slope ADC or ADC, this kind of ADC in a single acquisition, in a single signal processing. Because in the signal processing, we need to handle with lots of data together. What we should use in a voltmeter. Why only one signal, we measure one by one. Now, so this is How we already proved that this T2 is equals to input voltage. T2 is equals to input voltage, proportional to input voltage. Now we'll see how we can get this measurement. Okay. So if the input voltage changes, this input voltage again, another important thing is here. So this input voltage, if I draw this slope again like this, this T1 is fixed for the dual slope ADC and the reference voltage is fixed, right? Now if your input voltage change, what will happen? So your T1 T will change, right? So if I draw, if my input voltage changes, like this, if my input voltage increase more, so maybe my drawing is not perfect, but what I have to tell you that from here, if your input voltage changes, your first slope will increase. If your input voltage increase, your first slope will increase. If your input voltage decrease, your first slope will decrease. But the second slope will not change, because in the second slope, it is actually from what? It is from V reference by RC. Those values are fixed. So this slope will not change. Slope is same. But here you can see the slope is increasing at the input voltage increase. So if the input voltage changes, the first slope will change. If the voltage increase, slope will increase. If the voltage decrease, slope will decrease. But the second slope will not change. As here we can see two slope, that's why it is known as dual slope ADC. Here we can see it is a two slope. So that's why it is known as dual slope ADC. So in such a way, time T2 gives the direct measure of the input voltage. So here the equation is T2 is V in, or T2 equals to, we can write down T1 into V in by V reference. But these are two fixed. But this is the channel equation. So the T2 equals to corresponding to our input voltage. Okay. Now, if I draw the whole circuit now, so is it clear, everyone? Okay. I will hand over, upload this handles. Okay. So if I draw this circuit again, starting from here, so we have resistor, then give it to the integrator circuit. This is the output of the integrator circuit. Then we give it to the comparator. Then the output of the comparator will give it to the AND gate. And the AND gate output will give you to the counter circuit. And then it will give you some binary output. And the output of another input of this AND gate is our clock signal. Here we give this one, we have a switch, so that we can connect either V in or V reference. In the single slope, if you can remember, we give the input to this comparator out. Now here we are giving input from here. So this also connected to the ground, this one also connected to the ground. So here, output of the connector, integrator connected to the comparator. So at first, the input of the input, integrator connected with the input voltage V in. Okay. So at first, which one you give? Input signal. So it will give integration of the input signal. And this one is given to the negative. So it is already negative, and now it is given to the negative. So negative and negative will become positive, it will become high. So when it is high, the clock will fade into the counter. Counter will start to count, and it will keep counting until some point. Is it okay how the counting starts? Because we give at the beginning, we connect the switch to the input signal, input voltage, the sampled voltage that we sampled, right? We sample some voltage. In our last class, we discussed some voltage, maybe 6.3 volt, 3.2 volt, any of the sampled voltage, quantized voltage. Then we give it to this integrator circuit. It will integrate your input voltage. So it will, as this is a positive, so it will give you a negative slope. Now this negative slope input voltage is given to the negative terminal of the comparator. So it will become positive, so it will give it high. So when it is high, the AND gate will fed the clock. So we are trying to give the clock signal through this AND gate to the counter. So this input should be high. So when it is high, the clock signal is fed to the counter. Counter will start to counting. Okay. So it will count. There is another circuit in the counter is known as, in the counter circuit, there is another bit called overflow bit. Overflow bit. So for example, if we want to get a resolution for 4 bit, if you take a resolution of 4 bit, that means it will start counting from 0, 0, 0, and it will keep counting until 1, 1, 1. After it finishes counting, then what will happen? Then this switch will connect to reference voltage. If you think about our curve, it will like this, right? Then it will start to going. This is my T1. As I mentioned, T1 is fixed. So we'll get to T1 here. This will start counting from 0, 0, 0 to 1, 1, 1, 1. After that, it will switch to reference voltage. So we'll reach here now. So after all ones, during the next clock cycle, the overflow bit will become 1. It will generate, the overflow will generate 1. When it will generate 1, it will say that the switch now turn to reference voltage. Okay. So from going from all 0 to all 1s, how many clock cycle we need? 2 to the power n minus 1. Because 0 to 15, right? 2 to the power n minus 1. So it will require clock cycle. And if we include that integrated circuit of this overflow bit, it will total 2 to the power n pulses. Fine. So we reach to, now we are here in the reference voltage. We complete our counting. Okay. So now the reference voltage will get integrated. As the reference voltage is negative, right? My reference voltage is always negative. So integrated start integration in the positive direction. So it will start to integrate in the positive direction, right? But still it is high. Still it is high. Because still it is not reached to 0. Still it is high. If it is still it is high, that means still the clock process is given to the counter. That means counter is still counting. That means you are now counting. And we'll count until when? Reach here. Once we reach here, then counting will stop. So that means that T2 times is actually giving our information of the input voltage. So this is T2. As I mentioned, in the dual scope ADC, this T1 is fixed. So this T1 is this time. So that's why it is fixed. So you already know it's a 4-bit. So it will take 2 to the power n minus 1 clock cycle. So this is fixed. Now once it is come back, that overflow bit will generate 1. This switch will connect to reference voltage. Then reference voltage will try to reach to 0. At this time, still the output of this comparator is high. So still the clock signal is going to the clock counter, and the counter is still counting. Once we reach to this point 0, then they are equal, then we will stop the counting. So at that point, the output of this counter is equivalent to our input voltage. So this is how this dual slope ADC works. I hope I make it easy, understandable, clear? So as I mentioned here, after generating the overflow bit, when the reference voltage is getting integrated, this counter starts counting. The counter starts counting from 0 to onwards, and it will count until the output of the integrator is equals to 0. It will keep counting when? It will start counting, and it will keep counting until our integrator circuit output is equals to 0. This reference voltage. So now the clock pulse will not apply to the counter. At the time, whatever the binary output of this AND counter, it will be directly proportional to our time t. So we can say that binary output is proportional to the input voltage. So here, what is the total conversion time? This is important. The total conversion time is this one. Though we are saying that T1 is fixed, but it's not meaning that we don't require this moment. We require this time. So total conversion time is T1 plus T2. So as we are talking about this total conversion time, we denote it as TC. So TC equals to T1 plus total conversion time. So in general, for this total conversion time, it writes like this. If I remove these things now.
Doesn't this process make it slow?
Yes, this is I mentioned. Now, this is the drawback or disadvantage of the dual slope ADC. We cannot use this dual slope ADC for signal processing. We can use like a digital multimeter, where only one input you give just one, you just connect with your in between the voltmeter, right? To measure the volt, that particular volt. But it will give you accurate value. It will give you accurate value. So this conversion time, we can denote it by this conversion time like 2 to the power n Tc plus T2. Because here they need to go from 0, 0, 0 to 1, 1, 1. So this is the T1 time, then T2. Okay. So total T total in general is written as 2 to the power n Tc plus n time of Tc, number of counting. Okay. What will be the worst case? The worst case will be if T1 is equals to T2. That will be the worst case, right? So that will be the worst case. Or we can say that if the input voltage is equals to the reference voltage, if the input voltage is equals to the reference voltage, that will be our worst case. So in that worst case, this equation will be 2 into 2 to the power n Tc. This is the worst case. When the input voltage is equals to the reference voltage. Okay, so for example, just one example, if I give you an idea, a 12-bit ADC, a 12-bit dual slope ADC, a dual slope ADC, and the clock frequency is given. Clock frequency is given 10 megahertz. So in the worst case, what will be the conversion time? In the worst case conversion time, is equals to 2 to the power n plus 1 times Tc. So if you 2 to the power 12, if you put the value 2 to the power 13 and put the value of 10 megahertz, it will give you 0.8 millisecond.
So
if we increase
1 by T we need to put,
yeah,
1 by F we need to put in the Tc.
in the frequency. So if you increase it to 16 bit, it will become around 13 milliseconds. So that means if you increase the number of bits, it will get more and more time. So this is the drawback. This is the drawback of our dual slope ADC. So Dual slope ADC is good accuracy, noise immunity, it independent of RC. This is the advantage, independent of RC, good accuracy, noise immunity. But disadvantage is we cannot apply high resolution, and also we cannot apply for signal processing. The application is limited. So now I will take a small break and we'll continue. We have two more ADC technique. One is successive approximation, another is called flash ADC. Just give me 5 minutes break.
Professor.
For this dual slope ADC. Okay, for dual slope ADC is fine. Okay. So let's start about the second technique of the analog to digital conversion. It is known as successive approximation register, or SAR. In short, we call it SAR ADC. Successive approximation register. SAR. So let me first draw the circuit. This SAR ADC consists of three things. One is the comparator, another is the register itself, and third one is a digital to analog conversion. Though we are doing this analog to digital conversion, but here we need to digital to analog conversion circuit. So let me draw this circuit first. So we need three things: a comparator, a SAR register or successive approximation register, and third one is the digital to analog converter. So this is the circuit. This is the SAR approximation register. Give it here. We have the clock signal here. This is the comparator circuit. Here we will give our input signal, the in. This is the comparator. And output of this DADC will be given to another input of this comparator. So digital to analog converter, DAC. For here we have to give some reference voltage. So this is the overall circuit. It's a comparator. Output of the comparator will connect to the or given to the SAR register. In the SAR register we will have a clock signal, and from the SAR we will give the output to the digital to analog converter. And the output of digital to analog converter will be given to the another input of the comparator circuit, and will take the output from serial binary output from here. Okay. So here we are talking about this analog to digital conversion, right? So we have our sample and hold circuit. In the sample and hold circuit, it is sampled and hold. We need to hold circuit. We need to have some capacitor, because so that we can do some rest of the conversion. So here we do the conversion period. So during the conversion, we need to make sure that the input voltage that we are giving here, until conversion finish, that voltage will remain fixed. That's why we call it simple and hold circuit. In the previous part, from here we will have sample and hold circuit. So already see the sampling circuit, the sampling frequency. We have a low pass filter, two low pass filter to remove the aliasing frequency. Then we have to have the low pass filter that will be equivalent to the cutoff frequency, so that we can get back the same frequency. Then we'll have some capacitor so that we can hold our sample voltage Now this is the sample and hold circuit. So we give it to the input over here. So here, let's say if we want to understand with one example, let's say we have a sample input. Whenever we sample the input voltage, this input is equivalent to, for example, 11.2 volt. This is my sample input voltage. And let's say the V reference voltage is 16 volt. Because these are fixed, so give it 16 volt. Okay. So when the new conversion will start, this SAR, that means successive approximation resistor, will set the MSB to 1. We'll set this is the MSB, this is the MSB. It will set to 1 and rest of the bit will 0. When we start the conversion, it will set like this. So that means from the SAR we are giving to the input to the one, our digital to analog conversion circuit. So in the digital to analog conversion circuit, we give the fixed reference voltage is 16 volt. Now we are giving it to here. So that DSC will compare with this reference voltage and give some output voltage. Right? So what that equation? This equation, if I write down the equation here, the output of that tag is equals to V reference times. So if we are think about 4-bit conversion, 4-bit data, so we can think about B0 by 16, B1 by 8, B2 by 4, B1 by 2. We can think like this way. If you are not agree with this, we can put in different way, like B1 first, B1 by 2, B2 by 4, B3 by 8. So 1, 2, 0, 1, 2, 3. Sorry, this one 3, right? I'm sorry, nobody telling me that I'm right. No. So 3, 2, 1, 0. So the next significant bit will be most small one, and the most significant will be the higher one. Okay. So as I mentioned here, we are giving 1, 0, 0, 0. So what does it mean? If you put the value of reference voltage is 16, then we give the B0. B0 is 0, right? 0 plus 0 plus 0 plus 1. So this one we can think about by 2. Right? 1, 0, 0, 0. That's why I write down here. You can think about this way also. 1, 0, 0, 0. That's why I mentioned both, okay? Whichever you prefer. You can think about 0, 0, 0, 1. So, or you can think about 1, 0, 0, 0. Whichever is preferred to you. The same thing, okay? So, it means it's giving you 16 by 2 is equals to 8 volt. That means this 1, 0, 0, 0 is equivalent to how much? 8 volt. 1, 0, 0, 0 is 8. If I think that 0, 1, 0, 0, so if you put 0, 1, 0, 0, 0 plus 0 plus 1 by 4 plus 0, right? 16 by 4. So it will give you 0, 1, 0, 0 will give you 4 volt. Similarly, if it is 0, 0, 1, 0, 2 volt. If it is 0, 0, 0, 1,
1 volt.
right? So it's fine.
Like, don't we have like scientific laws of like it's
No, I just mentioned if we have. I just mentioned if we have 1 here, if you have 1, 0, 0, 0, it will give you 8 volt. If you give 1, 0, 1, 0, 0, it will give you 4 volt. If it is 0, 0, 1, 0, it will give you 2 volt. And if it is equivalent to 0, 0, 0, 1, it will give you 1 volt. This is the way. Okay. Now I don't know what will be there. So it's still like we didn't start the conversion. To start the conversion, the technique now will go move forward. So we have two things in the DAC. One is my input, one is my reference. This is, you can think about input voltage, right? Now we will start the conversion. The step is, at first, as I mentioned, when we start the conversion, it will start to set M is equals to 1 and then rest all will be 0. Then it will give it to the DAC circuit. In the DAC circuit, we have two input, one is V in and another is V reference. The rule is, if V in is greater than V reference, if V in is greater than V reference, then E of MSB, the bit will remain same. That means we are checking this input with the reference voltage. If it is 100, it is equivalent to 8 volt. If this 8 volt is greater than your reference voltage, it will kept. If it is not, we will change. Okay? If V in is greater than your, sorry, I make a mistake, so give me time. V in, oh, we didn't mention about the V in. Sorry. Oh, V in is here. And this is the given, and it will give you equivalent how much? As I mentioned, this 8 volt, right? This 100. If V in is greater than your VDAC, sorry, it is actually VDAC. If V in is greater than your VDAC, this digit will remain same. We'll keep this one. And then we'll change our next bit. We'll change our next bit. So at first we give 1000, so it will equivalent to 8 volt. So in the comparator it will compare 11.2 volt to 8 volt. So V in is greater than VDAC. So we'll keep this one. Then we need to check the second bit. So it will we'll keep this one, then we'll change this one to 0 to 1. Now we'll give it to 1100. So 1100 will be what? 8 plus 4? 8 plus 4, 12, right? Now it will become 12. If I'm not wrong, let me make sure. Let's see. Yeah. So now it is here now 12. Now my V in is less than VDAC. If it is less than your input voltage is less than your VDAC, then we'll reset to 0. We'll reset to 0 and check to the next bit. So next bit will become 1. Now it is 1010. 8 plus 2, 10. So now here we have 10 volt. So now it will again compare. Now you see 11.2 is greater than 10 volt. So again V in is greater than VDAC. So previously it was checked 1100, but it will remain 1000. Now we are checking 1010. So it still resets, so it will kept. Right? It will kept because it is still V in is greater than VDAC. Now we will check the last bit, LSB. 1. So 1011, 11. We put it 11 volt. Still V in is 11.2. So my V in is still greater. So V in is greater than VDAC. So it is kept, right? Now 1011. So what is 1011? 11. So you get 1, 0, 1, 1. We give how much input? 11.2. We are getting almost 11. This is the quantization error, 0.2 volt. 0.2 volt is our dead quantization error. So we are giving 11.2 volt. We are getting equivalent 1011. 1011 is 11. So that's how we can convert from analog to digital by using this successive approximation ADC.
Then what is the use of B reference here?
If you change the pre-reference, so it will then you have to compare the pre-reference. Otherwise, here if you take this 8 volt, then it will be 8 by 8.
Oops, sorry.
we can put any reference voltage here. So that if you want to talk about the digital to analog converter, it will be not here, but there will be some reference voltage so that you can compare that. So, but you can, it's not like that mandatory if you have to give 16 volt here. So step size will use. Okay. So this is how we can use a successful approximation conversion. What is the conversion time here? So what is the few important things here? So the first thing, basically it started from the most significant bit. So it will start always comparing from the most significant bit. This is the first step. It will check bit by bit. But this checking will start from the most significant bit. First. For each iteration, the ADC will take 1 clock cycle. So this is the clock cycle. For each iteration, it will take 1 clock cycle. So for 4-bit ADC, it is a 4-bit ADC, it will take 4 clock cycle. If you want to increase your resolution, it will take 8 clock cycle. So in general, for n-bit ADC, it will take n clock cycle. For n-bit successive approximation register ADC, it will take n clock cycle. So conversion time is how much? For this case, conversion time, total conversion time is n times t clock. N is the number of bits. So 4 times 4 clock cycle. If you increase the number of bits, 8 bits, it will be 8 clock cycle. Yes.
It just increases a bit and then brings it back down to 0 when it realizes that.
So if you increase the bit, it will reduce your the quantization error, but it will take time. Because for example here we have 4 bits, right? To get this 4 bit, we already get 11.2, we already get 11. So there is some quantization error. So in our last lecture, we already see that if you want to get more accurate value, we can increase our bit number, the resolution, 2 to the power n, 2 to the power, so n equals to 2, n equals to 3, n equals to 4, right? So this is how we can increase the resolution. If you increase the resolution, it will give you more accurate value, but of course there will be some limitation. For example, here the resolution for successive error, typically it is 8 to 16 bits. Typically it is only we can use 8 to 16 bits, like 2 to the power 4. And conversion speed maximum achievable is 2 to 5 megahertz per sample per second. So what is the advantage? High accuracy, low power consumption, easy to use, and low latency. Are you confused here or did I get a question?
Yeah, it's just, you said that like for this one, the second bit would go up and it would go back down. It would do all that with 1 clock cycle?
No, it is for each iteration 1 clock, second clock, third clock, fourth clock.
Okay.
Each time it's 1 clock cycle. But it will give you the data at the same time. So for first sample, it will give you 1. Then for the second is 0. For the third, it will be 1. For the fourth, it is 1. So in total, it is giving you, that's why the clock cycle is 10 times clock cycle, number of bits. So here, how many bits? 4 bits, so 4 clock cycle. So if you increase your bits, 8 clock cycle.
Okay.
But advantages, it will also have high accuracy almost, because here you can see it is 11.2 is equivalent to 11.1011. It is low power consumption, it is easy to use, and another one is the low latency time. What is low latency time? Latency time means it is the time between the beginning of the signal acquisition and the time when the data is available to download, the total time. So this latency is defined in seconds, and in the sample that is available within the conversion cycle, then we can say that the ADC has 0 cycle latency. So usually ADC has this SR ADC is a 0 latency circuit. So this is the, so typically we use this SAR. Please give me extra 5 minutes. I hope I can finish the flash ADC as well. The last one. Or we can continue, no problem if you don't complete. But let me start. The last ADC technique is known as flash ADC, or it is also known as parallel ADC. Flash ADC or as well as parallel ADC. In the flash ADC, we need three things. We need three things. It is the fastest, before the circuit, going to the circuit, it is the fastest ADC among all the ADC. It is the fastest. That's why it is also known as parallel, because it will take all the input parallelly. It will take all the, in case of SAR, we take one input at a time, right? One input at a time. In the flash ADC, it will take all the input at a time. That's why it is also known as parallel ADC. And this is the fastest ADC among all ADC. Okay. It requires three things. One is comparator. Then we need voltage divider circuit. So voltage divider circuit means we need some resistance. And we need an encoder, a priority encoder. How many we need? We need 2 to the power n minus 1 encoder. We need 2 to the power n resistor, and we need 1 priority encoder. But if we increase the number of bits, then we need to increase the priority encoder. For example, if it is a 3-bit flash ADC, so 2 to the power 3 minus 1, 7 comparator, then 2 to the power 3, 8 resistor, and 1 priority encoder. So if we have these three things, we can design our flash ADC. Okay. So we don't have so much time. I will go this working principle later, but let's discuss with what is the advantage or disadvantage of these things. Here in the flash ADC, the resolution is limited. Typically 8-bit. I am giving the example of 3-bit. If it is an 8-bit, 2 to the power 8 minus 1. How much? 255, right? If I'm not wrong. 2 to the power 8 means 256, right? 255 comparator necessary. So it will take huge space. If you want to increase the number of bits, it will take more space. So this is the limitation. Typically, the resolution size of the flash ADC is 2 to 8 bits. Okay. Then again, it is required more resistance level, right? So if you go for 2 to the power 8, that means you need to have 2 to the power 55 resistor of the same value. So this is another drawback. This is a resistive, so then power consumption will be high. So this is the drawback. But still, it is the fastest one. So while we use this flash ADC, we usually use this flash ADC for the large bandwidth application. For example, satellite communications, radar processing, and the oscilloscope. So here we use the flash ADC. As in the flash ADC, we'll see in next class, we can give all the inputs together. That's why it will be the fastest, and that's why it is known as parallel ADC. So in the flash ADC, we will need a comparator, voltage divider circuit, and the priority encoder. So thank you so much. We'll continue.